Hello, everyone. In this lesson, we're going to go over VSEPR theory. So, great review from grade 11, so valence shell electron pair repulsion theory, and figuring out based on electron repulsion how a shape of an atom, rather of a molecule, might look like. So, let's get started. I won't go in presentation mode. Oops. Okay. Okay. So we would review based on quantum numbers, I believe. Let's give this a shot. Might as well, as if we're in class. All right. So a few clues. So this has nothing to do with VSEPR, just review of quantum numbers. So this is a liquid. It's a mysterious element or a mystery element. So a liquid, it has the following quantum numbers. So n is equal to 6, L is equal to possible, right? 0, 1, 2, 3, 4, 5, although we know that 4, 5 aren't actually true. And ML is this possible range. So it doesn't give you an exact location in the periodic table, but those are those sets of quantum numbers. Something else has a positive 2 or 1 valence charge. And last suborbital is 5d10. I think that might give it away. So last suborbital is 5d10. If you're thinking about the answer, you can pause, try to figure it out. This is a pretty good review of quantum numbers and trying to figure out what element this might be. I think these last two, liquid and last suborbital, may have given you the answer, really helped to figure out the answer, and it is mercury. There you go, Hg. Okay, so let's continue with VSEPR. So I'm not going to read all of this, you can read it to yourself. Essentially what's happening, the points behind VSEPR theory is that electrons are negatively charged. They will therefore repel, right? Like charges repel. Negatively charged, they tend to repel. They don't like to be close to each other. Right? And this repulsion allows for the prediction of certain structures of molecules. So the shape of structures, the angle and the distance that atoms that exist in a covalent bond can come close enough to. So that's a distance, or between other bonds exist at a distance, at an angular distance away. Okay, so um, there are different forms of different amounts, magnitudes of repulsion based on high electron densities. We'll refer to that in just a bit. We're going to look at total number of electron pairs in two different ways, both bonded and non-bonded pairs. That's electrons that exist as bonds and electrons that are lone pairs of electrons that are not part of bonds. These two types of pairs of electrons will determine the shape of a molecule. And there's a strength of repulsion. So starting at the very bottom, between two shared pairs of electrons, or between two bonds, electrons certainly repel. They repel a little more if we have electrons that are part of a bond and electrons that are not part of a bond. Let's draw an example. A typical example here. Okay, so let's draw ammonia. I'll draw it in this form you've seen before, Lewis structure diagram or line diagram. Okay, so that is ammonia. All right, so shared pair repulsion would mean a repulsion between an NH bond here and another NH bond here. They certainly repel, not as much though as a shared pair lone pair repulsion. So that would be between, let's say, this one here. So here's a shared pair. These actually are made up of two electrons, and a lone pair. So they repel more than shared pair. Now here, lone pair, if ammonia doesn't in this case, it certainly does it, but if it had another pair of electrons resting here, they would repel the most, right? They're not confined to any kind of a bond, so they repel the most. So there is a certain order of repulsion. Okay, time for art and science. So as we've seen in previous topics, this is how you generally will determine the VSEPR shape and then how to draw the VSEPR shapes. I'm not going to read this out to you. Let's just jump into an example so we can put into context. Before we do that, this is a chart you will use to determine the VSEPR shape. I have posted this chart in our class notebook. Go to Unit 2, the Unit 2 tab, and normally we just have I believe it's just 3 tabs, so lessons, homework, and labs. I've added a 4th tab that says VSEPR charts. There's only one file there. It's this right here. Now, normally, you'd have to memorize all of these. So from rows to, well, this is the first row for all the rows. In grade 11, it was the first 3 rows, so 1, 2, 3. In grade 12, you'd have to memorize rows 5 and 6 or steric numbers 5 and 6 as well, so all of it. So you won't need to do that given our distance learning right now. You'll have access to this VSEPR chart. As long as you know how to use it, you'll be able to use it. Okay. If you've taken my class in the past, which I know a few of you have, if you're in my grade 11 class, you're very familiar with this. If you haven't, let's go over a few parts. So highlighter again, steric number may be something that you haven't seen in the past. So steric number 2, 3, 4, we'll define what that means in just a moment. What you'll also see here is 2 things you're going to see in every diagram here. A certain steric number, and then at the very top, a certain number of lone pairs. So we can have 0 lone pairs, 1 lone pair, 2 lone pairs. All you do is you match up the steric number to the lone pair. So for example, steric number 4 with 1 lone pair gives you trigonal pyramid. That is the shape, and you'll need to know how to draw this. Now these lines and dashed lines and triangles, they mean something in 3D space. They represent something. What you will not need to know how to draw, maybe I'll get to that later, but I'll mention it right now. I'll remind in context again, I'll say this again, but for now, you don't need to draw the 3D representation for lone pairs of electrons. So you can see here that this is pointing in a certain direction or exists flat on your screen. These electrons, these lone pairs of electrons here, this set is coming out of your screen, whereas the dashed line goes behind your screen. You don't have to draw the 3D orientations of lone pairs of electrons, so that's one thing. The other thing is you don't have to also memorize, well, you don't have to memorize any of this actually for our purposes, but you wouldn't then also have to memorize the bond angles. You may in university, so you'll see that then, but for our purposes, you will not have to memorize bond angles, or you'll not have to draw or refer to bond angles, and you will not need to draw orientations for lone pairs. So it's only the shared pairs that make up the VSEPR diagrams. Okay, let's get to an example. Okay, so here's our example of a worked out VSEPR diagram, but it's going to help us figure out what steric number means. So steric number just means, I was at a highlighter, steric number 5 means that we have, it's essentially just the sum of lone pairs and bonds. So the number of bonds and lone pairs. In other words, bonds, I can also say shared pairs of electrons, right? Bonds. This is also called ligands, and ligands just means connections. So a couple new terms here. Ligands means a connection. Okay, so it's a sum of your ligands and your lone pairs, or your unbonded electrons. Here, in this example, we have a shared pair of electrons, in other words, a ligand, another ligand over here, that's 2, another ligand over here, that's 3, and another ligand over here, that's 4. And just above sulfur, the central atom, we have a lone pair. So 1, 2, 3, 4 plus the lone pair gives us 5. So this has a steric number of 5. Since we're here, let's talk about what these lines mean. So a solid triangle, I know in our chart they don't appear solid. I'll highlight that for you. See, they don't appear solid. They should be. They typically are. So this is solid here, right? So that means it's going out of your page towards you. Let's change back to pen. The dashed line means the opposite. It's going behind the page, away from you. These straight lines here, they just mean that they are in plane with the page. Okay, so that's what those lines mean. Let's do methane as an example. And here are the VSEPR rules, just copied and pasted from a previous slide. Right, just the background looks a bit different, but it's from that slide here. Okay. But let's get to our example. So methane, you'll need to be comfortable with, you need to know how to draw Lewis structure diagrams. That's the first step, right? Back to grade 10, how to draw Lewis structure diagrams, you'll need to know that. So methane looks like this, right? If you don't know, if you want a refresher, let me know. I can help you out with that. But methane looks like this. It's carbon surrounded by 4 hydrogens, right? CH4, back to our organic chem unit. We have an electron pair here, 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 and here. These are all bonds. Right, next step is figure out the central atom. Our central atom in this case is going to be carbon. Whenever you see carbon, that's usually the central atom. But once you've drawn the structure, the Lewis structure, you can pretty well determine, pretty much determine what the central atom is. There might be some examples where there could be 2 central atoms, and we'll get to those. You'll ask those questions, and we'll figure it out then. Okay, but usually it's pretty easy to figure out. It's usually the one that is surrounded by other peripheral atoms. Okay, and if it's carbon, if you see carbon, it's usually carbon. So in our example, in methane, back here, we have a shared pair here, shared pair here, shared pair here, and a shared pair here. Right, so 4 shared pairs, no lone pairs around carbon. So that means there are no lone pairs. There are 4 ligands, in other words, bonded pairs. So we add 0 and 4, we get 4. So our steric number is 4. So going back to our VSEPR chart, right here, it's going to be one of these. Let me erase what I've drawn here. Okay, so it's going to be one of these guys. Draw that better. Okay, so tetrahedral, trigonal pyramidal, or pyramid, or bent, or angular. Okay, so one of those. We need to figure out how many lone pairs there are, but I think we already know that, but I'll get back to that. Okay, so where are we? Okay, this step, yeah, you might want to redraw your Lewis structure just to space out everything, but essentially you're going to jump over to step 5. You'll see that with 0 lone pairs and at steric number 4, it is tetrahedral. That is the shape. I don't have a slide that shows you how I've drawn it, but let's do that now. Right, you can see that there aren't 6 steps, but let me add a slide to that. Well, here, I'll show you the 6th step. 6th step is you're happy. You're going to draw what methane now looks like. And let's add a slide so that we can do that. So carbon in the center, right? We have, so this is tetrahedral. We have one bond coming out this way, one carbon-hydrogen bond going out that way, another one at a certain angle, right? Has to be generally roughly the same as a picture in your VSEPR chart. Okay, you don't want to put these right next to each other. Then there's another carbon-hydrogen bond. Now this one's coming out at you. So you're going to draw a triangle and you're going to fill it in. So fill in this triangle. That means that this carbon-hydrogen bond is coming out at you, like that. Then you have another carbon-hydrogen bond, and you're going to draw dashed lines, kind of in the form of that triangle. And that's going out back into the page or behind the screen. So it looks like this. Okay, tetrahedral, and compared to your VSEPR chart, let's see, should be similar, right? We see that tetrahedral here. We have one straight bond, or not straight, but one flat bond here, flat against the plane of your page or screen. Another one here, another one coming out at you, another one going behind. So that's tetrahedral, and that's how you would draw that. Okay. This, however, this shape can change. If you were to rotate this in different directions and different angles, you get a different shape. This could be, let's see if I can highlight this and make it all just one. Where's group? There it is, group. Okay, I'm going to make this smaller, move it off to the side. I'm going to redraw this a different way, but it'll be the same tetrahedral shape. So I'm going to rotate this, let's say this direction, right? So this H here is going to go behind. Another way to draw this. Just trying to visualize this in my head right now. And if you've, surprisingly, if you've played video games, you, according to some studies, you have a slight advantage in how your abilities to view 3D objects. So I'm rotating this methane molecule, trying to fill in these triangles here, and it would be tetrahedral still, just drawn in a different way. So what I've done here is I've rotated it this way, so taken this hydrogen, put it down behind, and all these three now move up in front of you. So this, call this one is up here, 2, this one is here, 2, 3, that one is now here, 3, and this fourth carbon hydrogen bond is now just behind, right? So these are both methane, they're both tetrahedral, just drawn a bit differently. Okay, both would be correct, mind you, on a test. I'd have to look at this and see how you've drawn it, and we'll figure out how to test later. For now, just this is how you two ways of drawing a tetrahedral molecule. Okay, compounds with more than one central atom. So in grade 11, you didn't see compounds with more than one central atom. You only have to worry about one, but they can be drawn. This is, well, you should be able to tell me at this point, it's not methane, it's ethane, right? So ethane, here we have two central atoms. We have tetrahedral around this carbon, and we have tetrahedral around that carbon as well, right? Now, if we're going to draw this, follow this link, guys. It's you can create ethane, you can move it around. It's a great simulation here to view that. So I'm just going to create a new slide. I'm going to draw ethane for you. So I always start off by picking one of the central atoms, so carbon in this case, and just drawing that one. So let's just redraw a tetrahedral carbon and 3 hydrogens, right? 1, 2, 3. Just for now, we're going to finish drawing the rest of the molecule. Okay, so I know that I'm going to have a flat or in plane with your screen or page. I know I'm going to have another bond coming out, fill that in, another bond going backwards into your page or screen, like that, like this. Now, normally with this would be hydrogen, it's not, it's carbon, right? Because we're drawing ethane. Okay, so now let's twist your perspective a little bit. Here is one in plane, one bond that is in plane. So I'm going to draw another bond that's in plane, going out about there. Then another one would be your double bond, or not, sorry, I said double bond, would be your filled in triangle, carbon hydrogen there. And this one could be going then behind, right? And that would be ethane drawn, drawing both carbons in VSEPR, tetrahedral here and tetrahedral there, right? Okay, now VSEPR turns out that when two shapes, trigonal pyramidal shapes or trigonal pyramid shapes of these two substances were determined, it was probably using X-ray crystallography, just another method of visualizing 3D structure, the structures of molecules. Bond lengths and bond angles are actually not the same, not as predicted by their shapes. They should just be whatever trigonal pyramid says they are, but it turns out that it's not actually entirely correct. So VSEPR is a great approximation. I'm not saying this is wrong, this is absolutely correct. The details, though, just tell us, like many other, like this, that has been the theme for many other models, especially of the atom that we've talked about, or the progress of the model of the atom. Whenever something isn't exactly as expected, it usually means that there is more to it. We're going to get to that later on in other lessons when we look at hybridization. But turns out that VSEPR is still accurate, but it's not exactly perfect. Okay, so we're done. Your homework and posted online is a VSEPR Theory Practice worksheet. I believe there are answers for this as well. Give it a shot. Most of this is grade 11 review, so I'm hoping it's okay, but still post any questions that you have. See you later.